our last session before lunch, I'll promise this is going to be an exciting one. We have Deepak Shapeti, CEO of Morphing Machines, who will talk to us about a revolutionary semiconductor chip that they're working on, which can work on parallel processing, multi-core chip, which can support new workloads across AI, MLs, 5G, and 6G. And one quick thing about Deepak, Deepak's background is unique as what they're building. Deepak is a chemical engineer by training from Stanford University in the Valley. Worked on AI and drug discovery, had his own startup, worked on multiple roles, and about 2.5 years made a complete shift to semicon. And you will see how proficient he is with semicon right now. Deepak, over to you.
Thank you. Thank you, Sunil. A very warm good afternoon to everybody. I know a pre-lunch session on hardware, ouch. But I promise you this, you will savor your lunch a whole lot more if you get through this. So thank you, Sunil. Thank you especially for giving me the opportunity. I think before I start my talk, I would like to probably address one factor. A textile engineer doing biomaterials, chemical engineering doing the reverse. So I think Speciale has got a special eye. I don't know how they spot it because we told them post facto. So amazing job, guys. But with that, I think let me introduce myself. I'm the co-founder at Morphing Machines, and I think we'll get into what exactly we're building. But before that, I just want all of us to reflect on the marvels of our digital era. I mean, we take for granted the seamless connectivity, the fantastic, the wealth of information on our fingertips, the utility of ChatGPT, which we saw today in action, and immersive experiences which can extend our reality. Now, beyond this, behind this digital tapestry, there's a very well-coordinated dance of both software and hardware. And while software innovations, will catch the attention and, the fancy of end users, it is not the same with hardware. With hardware, it is hidden behind the scenes and abstracted away. And it is in that context that I want to bring to you the first heroes of the hardware industry over the past 25 or so years since the advent of the internet era. These we like to call as GP, or general purpose processors, as a background. So these are your CPU, your GPUs, which we all know and love, and these have done a great job. Typically, these general purpose processors are exactly what they, the name purports to be. They're general purpose. They're flexible, and they can do a myriad of tasks, from document spreadsheet editing to gaming to web browsing, video, anything you want to think of it. And this has been critical in fostering and getting us to where we are today, especially for the software ecosystem, which did not have to worry. Either application developers could just develop something, deploy it, and most of the times it would just run well enough. So this was the whole background of how compute was earlier. But today what is happening is compute demand is exploding. Okay? And what I'm going to focus on today in my talk, beyond just a revolutionary processor or a processor platform, is how can we democratize and reduce barriers to hardware innovation. We hear a lot about software innovation, about reusable building blocks, open source, all of these components. Where is that for hardware? There are some elements, but the large portion of that ecosystem is still yet to come. And all of this will lead to sustainable innovation in the hardware space. Typically, whenever someone builds a groundbreaking software application, the barriers to entry, some engineer could do it sitting in a garage. I mean, not so much anymore, but with cloud, maybe yes. But the same is not true for hardware. And why is that? Of course, it is deep tech. People will tell you that, but there is still opportunity for doing that innovation. And that's what my focus is going to be today on. But a little bit of background, right? I mean, what is the problem and why do I want to do sustainable innovation at Morphing Machines? I think that background we need to first have. So the past, I think from 1967, since Fairfield Semiconductors was incorporated all the way till 2018, there has been a phenomena called as Moore's Law in semiconductor industry, which essentially is a fancy way of saying that, hey, every 18 months we can miniaturize the building blocks of processors, which are essentially transistors. You miniaturize that, and what does that do for us? It essentially gives us a cheat code. It allows us to double performance, reduce power at the same time every 18 months. And that is the beautiful curve you see on the topmost, right? I mean, the transistor line, which is going on beautifully. But come 2018, this pace slowed down dramatically because we're finding it more and more difficult. There's a physical limit to how far you can shrink. And in 2020 onwards, it has practically become, the pace has become almost negligible or it has stopped. So the cheat code of being able to double performance and reduce power every 18 months, rather not even 2 years, has gone. What does this mean? It means the cost of cloud compute will go up, the cost of your 5G network, the cost of communications, anything which you're used to in terms of our digital footprint today will climb in cost. The reason why costs have been declining for digital is because of this compute innovation behind the scenes. Now with that gone, what do we do? Okay, where do we go? So we are left with a couple of things. We are left with what we like to call as parallel performance. We can't miniaturize stuff, so hey, can we put more of those compute elements and parallelize stuff? Let's put it in parallel. Like instead of having one hose, why can't we do some 10 hoses in parallel? That's the essential concept. And at the same time, see how we can innovate in terms of power. Now, these specifically are called domain-specific processors. So this is what has been driving in the last 5 years a move away from general-purpose processors, which is the CPU and GPU we love and which are very much going to stay, but they are growing at a CAGR of about 10 to 11%, a compounded annual growth rate. Whereas the domain-specific specialized custom processors are growing at a CAGR of 55%. Speaks for itself. The reason is because we don't have that cheat code anymore. So we have to keep on increasing compute because generative AI or other AI, communications, everything has just exploded the requirement for compute. You're seeing $1 million servers in the cloud, but no way to scale beyond a particular power or a compute limit today. And that's where these custom processors become very critical to furthering hardware innovation down the line. A fact about the computer, chip development costs, right? This is not manufacturing cost, this is not fabrication cost, just the design cost. When you're creating a custom SoC or a custom system on a chip, which incorporates a whole lot of custom processing elements, which I talked about, which have increased in the recent years, from Qualcomm's chips to Apple's chips to any chip, NVIDIA's chips also, if you think about, all of them have these custom compute elements in there. But basically, what has happened, what has stayed uniform, is as this miniaturization cheat code has disappeared, the cost of design has gone up dramatically. Today, we are talking about, we're in excess of $300 million for design of one custom processor at the minimum. And this is the lower end I'm speaking. This could very well go beyond, in some cases, some system companies like Apple, they spend over $1 billion to do one chip of theirs. But if you're talking about vendors or semiconductor companies, typically it could be upwards of 500 million for more advanced chip. And this cost stack, as you can see, is spread over a series of components, including software, physical verification, and all of that. I won't go too much into detail on that, but it is an accepted phenomena today that high cost is a must-have in order to develop an efficient processor today. Otherwise, you cannot cut it. Now, what about the democratization which I started off with earlier? How do we do? So at Morphing Machines, our goal is very simple, that hey, all of this is good when you're going, why can't we try to take some of the lessons from the software industry? And please, for all the semiconductor folks out here, I'm doing a little bit of reductionism, so take it with a grain of salt. But the way we are doing it is we are increasing reuse, and we're reducing the components. Wait a second, sorry. Yeah, we're reducing some of the stack here. We are making it disappear, or we're automating it such that you don't have to do that expenditure again and again. And we want to bring down the cost of development from $300 million to under $5 million, and time of development, which is another fact, time and complexity. These two factors, typically, time will be anywhere between 18 to 24 months. And this is for companies like Intel and Qualcomm, who have an army of highly trained engineers, not for mere mortals like us. So, even in those cases, it is 18 to 24 months. And with complexity involved, easily cost balloon over $500 million. So we want to bring it to 5 months and below 4 months of execution time. And how do we do that? Right? But before how do we do that, I think one of the things is why it is happening in India. I think that is a very important part, because there's a lot of, before we met Speciale and Vishesh, right, and Sunil, the question asked was like, why is this not being done anywhere else? Okay? Or why is it happening in India? I think one of the primary reasons is capital efficiency. Ample risk capital is not available in India. I wish there were more Speciales. Hopefully there will be. But I think the ability to see something and fund it has been a big constraint in India. And what that has done for the entrepreneurial mindset, and I'm sure my other founders will also agree to an extent, is optimize and be very careful about how you deploy your capital. Certain things are off the table from day one, like high capex intensive projects are off the table right away. Now, how can we innovate in order to enable other ecosystems? So we work on the business plan very hard. So I think that has been one of the primary reasons why innovation or deep tech in India is taking a slightly different route than typical or traditional deep tech. The second one is we have access to a world-class hardware and software talent, engineering talent. So that makes it a very good starting point that we don't have to create an entire ecosystem and educate skilled manpower in this space. And lastly, the domestic consumption volumes are a big, kind of a mitigating factor for us. We don't have to break through in a go-to market. We don't have to break through the global market immediately. We have the luxury of first catering, supplying, testing our products in India, and then going global. This is a luxury not every other country has. So these three things, combined with the geopolitical scenario and Indian semiconductor mission's thrust, have all of come kind of. It's a confluence of all of these factors to make sure that, hey, we can innovate in the context of hardware, and especially in terms of semiconductors. Now, this is where I come to our processor platform. We promise that we'll reduce cost dramatically and time to market dramatically, time to design dramatically. How do we do it? So Redefine, our processor platform, is actually built up of modular building blocks, which are reconfigurable. Reconfigurable being the key word, because this allows us to use our processor block across industries, verticals, and applications. No more designing a custom processor only for one thing. So as my life sciences friends from the previous, last but one talk over there, they must already be using something for gene sequence alignment or for drug discovery, structure-activity relationship. Typically, those processors are modeled on very specific FPGAs, a type of processor. Now, with our processor, there's no need to do so. You can use it for life sciences, you can use it for AI/ML, you can use it for a whole bunch of other 5G, 6G communications as well. And it is this modularity that forms the building block of our entire processor platform. Essentially, what we're doing is a low-code workflow. If you want to equate it to the software world of things, a low-code or a no-code workflow where you automate a lot of the elements associated with that cost stack which you saw earlier. And let me give you an example. Very recently we had a chat with a integrated semiconductor major, and wherein a particular group was designing a multimedia chip. This multimedia chip is supposed to pass through video and process it at 4K resolution and at 60 frames per second. It just requires some amount of computation. It corrects for color, noise, grain, all the beautification stuff we see in either our cameras or our TVs, and so some such, right? Now, these guys had just done it for 4K and 60 frames per second. And within 12 months, the requirement has now been upgraded to 8K resolution and at 60 frames per second. Now, what this means is they need more efficient algorithms on the software side in order to run or handle that amount of data and compute. And at the same time, because the algorithms change, they have to now design newer hardware. So they go through that entire design cycle, and they mentioned that their timeline is about 12 months to do this, an incremental version of the same chip, and a cost of about running into tens of millions of dollars. Now, what would happen if you actually were to do that with us? That is where the value of a platform like us comes in. It is not just in the context of India, but frugal innovation and sustainable innovation in hardware is required. We cannot have every chip created at hundreds of millions of dollars. It's good for semi-majors, but if you want to truly democratize things, you need to foster innovation at a smaller scale. So this is a lot of detail, but I'll bring back that earlier cost stack that I had, and you'll see that we are able to eliminate this part. The one which is put into dark, we can eliminate it for that semi-major and essentially bring down the time of design for that new chip for the media group from 12 months to 1 month. Now, in a big company, this means at least tens of millions of dollars, in addition, faster time to market. And just think about what would happen in the previous thing, what would happen if you're already using our chip to begin with. If this major was using our chip for 4K 60 frames per second, which was the existing specification, and they came up to a new specification, 8K 60, they wouldn't need to do a thing. You could just run a software update over the air. Our chip is able to reconfigure itself in order to run the latest algorithms or the more efficient algorithms which your software engineers have come up with, and all is good, and everyone is happy, right? So so this is where the value of real-time reconfiguration comes into play. And as an example, I think 5G, 6G is a great example, because this is a very highly capital-intensive industry. Typically, network infrastructure deployments will run into tens of billions of dollars, and that is per mobile network operator. okay? And the way they recoup costs and all of that is it's almost as troubled as the airline industry in some sense of the word, right? And this is because CapEx is very high. On top of that, OpEx, that's the operating expense, is also very, very high. And the reason is they cannot optimize their network on the fly. They most of the times come up with custom processors which will allow you to implement a certain set of applications or workloads in a static manner. Tomorrow, if you're able to innovate and bring about an AI/ML algorithm, which is happening right now, which will improve, which will double the amount of users you can cater to from a single 5G tower, that is in the works. But that algorithm doesn't exist today. So how do you design hardware for that algorithm? With a reconfigurable processor, you don't need to. And so that is a whole use case that, hey, it's not just that we can reconfigure, but we can dramatically bring down CapEx, because for us, it is just a single piece of hardware, and we have a platform which enables end-to-end development and deployment. And along with that, it is not that you're only saving cost. And I think I come back to probably what Vishesh or Sunil were saying earlier, which is that it is not only about a cost play today in India of startups coming from there. We are giving you better compute than current options at a lower, lower power consumption. So not only that, in addition to that, we're giving you cost savings. So I think it's a confluence of all of these which actually makes it a really compelling, value proposition. And to wrap things up with, I think it's very important to call out that, a lot of people have talked to, a lot of people in the ecosystem were interested in investing, right? But most of the cases that we were asked about is why is it in India, right? Why are you doing it here? So I think in a sense, you need the right partner. So for us, Speciale has been that partner. They have not only just, not laughed at our crazy ideas, but have supported us not just with financial, but more importantly, network and intellectual capital. I think, founders need to be crazy enough to dream, but I think in some sense of the words, I find Vishesh, Arjun, and all of the whole team to be founders themselves, because they're equally crazy as us. And that's what makes, it's an ecosystem effort which makes it happen. And we're really excited for the future in semiconductors, boring as hardware may sound. Today, it is a very well-fragmented industry. You're the Intel, you're the NVIDIAs, you're the big players who supply chips and people just reuse them in their hardware. Why isn't there a local producer of chips? What is the barrier stopping? And now if you democratize it, what will that future look like? Like, hey, anyone from India can, device manufacturer, right? Whose revenues run into billions of dollars in India, like Dixon Electronics as an example. If they can for them, $2 million investment is nothing. If they can create their own chip in order to, have a local supply chain, what's to stop them? So the future will look very different in India, not just India, but globally as well, wherein you will see a host of new generation companies, from smart toy chips to battery EV management chips to industrial IoT, wherein the companies or the solution providers who right now are purchasing hardware off the shelf with this modular no-code or low-code deployment and creation platform will be now able to create a custom silicon. Hardware will not be a barrier to their product and cost today. It will not define them. What will define them is they'll transition from being a software or a software company to being a systems integrator, a systems provider like a Apple, or perhaps even a solutions provider. And that's the future we see in terms of mass innovation enablement at the ground level, when there's a whole bunch of solutions company rather than just hardware or software driven companies. And finally, I think the ecosystem has truly matured in India. Historically, India was known as a place where you can have great research, but the last mile of translation into products was missing. But that is dramatically changing. I think today, one of the biggest things, I'm happy that Speciale is going global, is we at least get a seat at the table. Earlier, that was not the case. We get a seat at the table, people will hear us out. And as long as we have a compelling value proposition to make, they'll lowball us, but still we'll get the deal, right? So that is something which has changed enormously because of the ecosystem enablers which have happened, in the last 5 years. And we're looking to, towards a great sustained hardware innovation future. And thank you, everybody.